All right, today we're going to talk about the van der Waals gas. So we talked last time about an ideal gas, and in an ideal gas, we're completely ignoring any interaction among the molecules. And there are a lot of consequences to that. One is if two gas particles come together and there's no interaction, it just means they pass right through. So if we have one particular gas molecule we're looking at, it's free to explore the whole container as if there were no other gas particles there. A secondary effect is that the interaction, it is the interaction among itself and among other molecules that determine the identity of the particular gas. So if there is no interaction, then there is no difference between any kind of gas when it's considered an ideal gas. And so we lose the ability to discern A from B in terms of how it behaves in the ideal gas laws. So we saw Dalton's law of partial pressures being one manifestation of that. Well, today we're going to talk about one non-ideal gas law called the van der Waals gas. This is the most important gas law besides the ideal gas law. There are certainly many other gas laws, and as we go up through the curriculum here, we'll study a few of those, and we'll study the van der Waals in much more detail. Today, I mainly just want to introduce the idea, give some of the basic concepts of what the non-ideal gas law would entail, and just to kind of get our feet wet with this. But it won't be, we won't be going really deep into this topic. All right, so let's remind ourselves with the ideal gas law, PV equals nRT, and I'm going to solve explicitly for P, because the van der Waals gas law is explicit in P. So what is the van der Waals gas? Well, let me write the equation of state. Directly here. So we see a term that is almost like the ideal gas, except that the volume, we're not dividing by the full volume, we're dividing by the volume minus something. And then we see another term that's coming in as a subtraction. And so let's first just look mathematically at what this is, and then we'll look at what is going on here. Each of these terms, this one, is characterized by a van der Waals B parameter, and this is characterized by a van der Waals A parameter. Let's just pick up the units quickly. So the units here, this whole thing has to be volume. So B is volume per mole, or a molar volume. Now, what that means, we'll interpret that in just a minute. And then A has a little bit more complicated units. It's a pressure times a volume squared over a mole squared, because this whole thing has to equal pressure. And so our volume squares will cancel, and then the mole squared will cancel. We can also write this as pressure over a concentration squared. So a little bit less intuitive than a molar volume, but we'll try to interpret it a little bit as we go along. Now, mathematically speaking, let's look at each term as compared to the corresponding ideal gas. So here's the ideal gas. Let's turn A off so that we only have this term. What we see is that we're subtracting something from the volume, and this would make the pressure be bigger for a van der Waals gas relative to an ideal gas if this term was turned off. Well, what exactly is this doing? This is subtracting some sort of volume. Can we interpret that volume? Well, that is the volume that n moles of gas take up in the container. So let's imagine this container here, and it's filled with the gas, and what we're going to do is just take all the space out between the gas. So effectively, we're going to condense the gas down to the bottom of the container, and then we're going to ask, what is the volume, what is the molar volume, then times the number of moles of the gas with no space in between. So basically, if we turn it into a liquid. And that's called the excluded volume. If we have a test particle here, then it's free to explore this whole container except where the other molecules are. And so this is a good representation of how much room a given molecule has. And so that's pretty easy to interpret. It's just the room that the molecule has. The more moles of gas we have, the less of the full volume of the container we have, and our pressure is going to go up. It's as if we are compressing the container for an ideal gas. Okay, so that's this first term. And so this is a excluded volume term. And so what's really this representing down at the molecular level is the fact that we can't push two molecules on top of each other. The ideal gas just lets them pass right through. That's not the case for a real gas. So we can't have two real gas molecules in the same point in space at one time. So that's what the B term is characterizing. Now, let's imagine B is 0. So we'll turn B off. Then this is an ideal gas. And then we're subtracting off a term that's inversely proportional to the concentration. So what is this? I'm sorry. This is concentration squared. So we're subtracting off a term that is this constant, this van der Waals A parameter, that is proportional to the concentration squared. All right, so that's this bit here. So what is that actually? Well, it's harder to intuit, but the intuition that we can develop is that the pressure is due to molecules colliding with the wall. So the molecules collide with the wall, that's what's causing the pressure. As a molecule is coming in towards the wall, there's an asymmetry in the distribution of other molecules around that molecule. There's more molecules on this side than this side. And so there is a very mild yet real attractive force in this direction. Not so much continuously, but as particles pass each other, the intermolecular forces that they experience act to slow down their relative velocity. So if we're going like this, there's a little interaction that's going to slow each of them down. Since we have an asymmetry in this direction, this molecule, any molecule that's heading towards the wall like this, has gotten slowed down relative to the case where it was an ideal gas. So this is all relative to an ideal gas where there's no interaction. And so the molecule sort of pulls its punch a little bit when it comes to collide with the wall, thereby reducing the pressure. So pressure here is reduced. Now, why is it proportional to the concentration squared? Well, right off the bat, I think we can feel comfortable that it should be somehow proportional to concentration. Because if the concentration was very small, this effect would be very small. And if the concentration was bigger, this effect would be bigger. So we would expect the degree to which the molecule pulls its punch and reduces the pressure should depend on concentration. Well, you can make kind of an argument, and it is a little bit of a hand-wavy argument. And at the end of the day, this is just an empirical equation. It is something that works well, and so we can't hope to rigorously build this up from scratch. We just want to try to gain a physical intuition. And so let's try to gain an intuition for this square factor. We certainly, I think, have an intuition for the fact that it's proportional to concentration. Well, the net effect of the other molecules on the molecule that's coming to collide with the wall should be proportional to concentration. But there's a back effect. So notice this this molecule affects this molecule, but this molecule affects this molecule. And so there's a net back effect of the molecules that are colliding with the wall on the remainder of the molecules. And I know this is very, very hand-wavy, but that will depend on the concentration. The number of molecules hitting the wall will depend on the concentration. So we get another factor of concentration, and it comes in as concentration squared. All right, so this is the van der Waals gas. It is, like I say, the most important gas law besides the ideal gas. And we've seen here where it's starting to, or at least we can explain some of the behavior or gain an intuition for some of the behavior. This then does bring in the properties of the gas. So oxygen has a different van der Waals A and B parameter than methane or water. And so there are these big tables of van der Waals parameters, and you can look those up, and they're different for different molecules. And so it's a way that the identity of the gas actually gets encoded into the equation of state. Very quickly here, just like we often want to write things in terms of intensive variables only, let's multiply top and bottom of the first term by 1 over n, and then let's just recognize this as molar volume. So we'll have, second term will be 1 over molar volume, which is intensive, and then the n here will, 1 over n will cancel the n up on top in the numerator, and will change volume into molar volume minus n over n. N's will cancel b. And so the van der Waals equation in terms of intensive variables only is this. The volume is replaced by molar volume, and then the n's are taken out of the equation. All right, so that's van der Waals equation. And so we don't have a lot of homework on this. Your book may or may not go into this. If it does, go ahead and read that section. They might have a few homework. I'll probably have a few homework questions in the notes. But mainly here, just get familiar with a gas law that isn't the ideal gas law and why we might want that.